Pizza. A food with Italian origins that is beloved by every person of all ages. But have you ever thought how exactly pizza is made? Why it is so perfectly round in its unperfected world? What rules did God use to make this masterpiece of his creations? The answer is pretty obvious. He used science. Having gone to a pizzeria, you may have noticed this amusing scene when the cook is tossing the dough up in the air and making it fly from one hand to another. It seems as if the cook is trying to entertain the visitors, however he is not. Well, at least not 100%. Tossing the dough in the air is the key to the mystery that is the perfectly round dough. And since we are scientists, let's think about the way in which we can explain this magic.
It all starts with a dough that was initially rolled out a little bit into a circle shape with center O and radius R.
But wait, hold on. Why on earth would you throw a dough into the air to stretch it when you can just roll it with a rolling pin?
The thing is that the dough can be described as easy to bend and easy to stretch, which means that we can change its density pretty easily by getting rid of the air bubbles inside. And that's what a rolling pin does. It gets rid of the air inside the dough. There are two ways of tossing a pizza. The first one is the horizontal one, when the dough is being rotated and tossed between both hands of the pizza maker, so that the pizza moves in a semi-eclipse trajectory. This method is preferred due to its easier control. Another method is when you throw your pizza straight into the air, rotating it with one hand so that it flies by spiral trajectory. In this case, when the cook throws up the pizza, they give it kinetic energy to move. As the pizza moves up, it loses some energy due to its air resistance. The rest of the energy is transformed into GPE. At this point, pizza starts falling back, accelerating due to the gravity of Earth.
Now for the fun bit, the rotation of the pizza. We can notice that the pizza continues to rotate even when it starts to fall. It can be explained by knowing the vertical and the horizontal angular forces do not affect each other. The pizza's central gravity is at O, and the force applied to it is horizontal. The pizza is in equilibrium. That means that there are a couple of moments or torque acting on it, and the pizza rotates about its center.
The tangential velocity of the pizza can be derived from a well-known and beloved Newton's second law, F equals ma. Anyway, from F equals ma, m multiplied on v squared divided on r, we can say that v equals f multiplied on r squared divided on m. So the bigger the radius, the faster the rotation.
But how does the pizza carry on spinning during all its flight? And how does the radius increase?
It is all because of such things as angular momentum. It is like ordinary momentum, which equals mv, which we all remember from our GCSEs, but it is also has radius in it. So angular momentum equals mass multiplied on velocity multiplied on radius. As pizza gradually slows down, its mass remains the same, so its radius has to increase. And that's how the dough is stretching nice and evenly.
Look at that. Using gravity to your advantage makes an awesome pizza dough.
Sharing pizza with a friend, but not sure you're getting fair shares? There's a guaranteed way to find out. For Rick Mabry and Paul Dearman, they can't think about sharing a pizza, for example, without falling headlong into the mathematics of how to slice it up. We went to lunch together at least once a week, says Mabry, recalling the early 1990s when they were both at Louisiana State University, Shreveport. One of us would bring a notebook, and we'd draw pictures while our food was getting cold. The problem that bothered them was this. If two people take turns to take neighboring slices, will they get equal shares by the time they've gone right round the pizza? And if not, who will get more? Of course, you could estimate the area of each slice, tot them all up and work out each person's total from that, but these guys are mathematicians, and so that wouldn't quite do. They wanted to be able to distill the problem down to a few general, provable rules that avoid exact calculations and that work every time for any circular pizza. The easiest example to consider is when at least one cut passes plumb through the center of the pizza. A quick sketch shows that pieces then pair up on either side of the cut through the center, and so can be divided evenly between the two diners, no matter how many cuts there are. So far so good, but what if none of the cuts pass through the center? For a pizza cut once, The answer is obvious by inspection. Whoever eats the center eats more. But for greater numbers of cuts, who gets more depends on the number of cuts. Assuming two diners, A and B, take alternate slices, and that the angles between adjacent cuts are all equal. If n is greater or equal to 4, then A and B get equal amounts of pizza. When n is 3, 7, 11, 15, and so on, B eats more when B gets the slice containing the center of the pizza. When n equals 5, 9, 13, or 17, and so on, B eats more when A gets a slice containing the center of the pizza. These three general rules sum up the pizza conjecture. Mabry and Dearman found a way to prove the pizza conjecture that involves comparing opposite slices in turn. Instead of looking at the actual slices, X and Y say, they drew a line parallel to each cut running through the center of the pizza. They then used the rectangular shaded areas as a measure of the difference in area of opposing slices. Plug that into some very complicated algebra and the proof arises. So, with the pizza theorem proved, will all kinds of important practical problems now be easier to deal with? In fact, there don't seem to be any such applications. Not that Mabry is unduly upset. This may ruin any pizza endorsements I ever hope to get, Mabry says, but I don't eat much American pizza these days.